Hello everyone, welcome to the third lecture of this course on microsensors and nanosensors. In the previous class, we were discussing the orientation of a wafer, and this orientation was classified by Miller indices. So we have also seen in short that how Miller indices are calculated for a wafer. So this Miller indices, the concept of Miller indices came in the way when we started discussing how to select a silicon wafer for the fabrication of my microsensor. And I also mentioned that just orientation is not enough for choosing the right wafer. So we should also know the type of wafer, okay? And this type is dependent on doping profile of the wafer. I also defined doping. What is doping? I mentioned that when I have an intrinsic silicon wafer and I introduce some known amount of impurities in silicon silicon crystal, okay, I say that I have doped my wafer. Okay, so this impurity is either from group 5 element or group 3 element. Okay, so you might be knowing that silicon is group 4 element and its atomic number is 14. Okay, so let us see that depending on which element is being doped into my silicon, the doping can be n type and p type. Okay, so just have a look on this silicon, say 2D view of silicon crystal. Okay, if I have to define a dopant, I can say that the dopant is a material that has been implanted in the silicon to change the type of the silicon. Okay, basically it is the impurity. Okay, so typically n-type dopant are phosphorus, arsenic and antimony. All these three are group 5 element. Okay, when I say n-type dopant means this will also make my wafer a n-type. Okay, and this word n is coming from abundance of electron because of this doping. Okay, so as you know that my silicon is, if I have a silicon, I have 4 electron in the valence shell. Okay, and if I am doping a group 5 element, the 4 electron from the outermost shell of this group 5 element will bond to this, and I will have 1 electron free, which is shown here also in this 2D view. Okay, and this electron is can hope inside this. Okay, and because of this my conductivity is going to change. Okay, so this is n-type wafer. Then I have a p-type dopant. As I have mentioned, a group 3 atom. Usually boron and gallium are group 3 dopants in my silicon crystal. Okay, these have 1 less electron and this will leave a hole in the silicon lattice which is free to carry current. Okay, so based on these dopants, I have n-type and p-type wafers. Okay, now I know the orientation and I know the doping. Okay, so I know my wafer is n-type or p-type and which orientation it is, 100 or 110 or 111. Okay, so I know the orientation and the doping profile of my wafer, and now I am ready to select my wafer. Okay, so usually based on doping and the orientation, I have various profile of this wafers. Okay, usually in laboratory we use wafers under 200 mm in dia. Like I have a 2-inch wafer, 4-inch wafer, depending on which lithography facility I have in my laboratory. Okay, in smaller wafers, anything less than 200 mm, a pair of flats at different angles are there which convey the doping profile and orientation of the wafer. Let's see some of the example. Okay, the first example is on 100 n-type wafer. Okay, just have a look. I have a bigger primary cut over here and a smaller secondary flat over here, and they are at 180-degree angle. Okay. So if you see any 2-inch wafer or 4-inch wafer where there is a bigger primary cut and a smaller secondary cut, and they are at 180-degree to each other, you can immediately say that it's a 100 N-type wafer. Okay. Similarly, for 100 but P-type wafer, they are at 90-degree, as you can see over here. Okay. Similarly, for N-type 111 wafer, these primary cut and secondary cut are at 45-degree, while for P-type 111 you have only a primary cut. You do not have any secondary cut. Okay. So by seeing these cuts, actually I can identify that which kind of wafer it is when I see the actual wafer. Okay. Resistivity and all are very difficult to identify from these wafers. I mean, you have to do electrical characterization to find the resistivity and all. So mostly these wafers comes in a pack of 10 or 12. On that pack itself, it is mentioned that these wafers are having this much resistivity. Okay. Wafers of 200 mm diameter and above uses a single small notch to convey wafer orientation. We will not discuss them. Okay. I think this much is more than enough for this particular course. Okay. So now I know that, okay, I have this wafer which is N-type doped, and this has this much orientation. It is 100 or 111 depending on what wafer I have chosen. Okay. And please remember that these orientation, I have mentioned that they are used based on the subsequent processes. What are the next processes? What I am going to deposit on this? What is the lithography technique that I am going to use? Okay. So based on that, I have chosen this. Okay. Now these wafers, be it N100 or P100 or N111, P111, anything, they are polished, okay, before it reaches the end user. There are two options for polishing. Okay. Either you have a single side polished wafer or a double sided polished wafer. We call it SSP and DSP. Okay. So you have single side polished wafer and a double side polished wafer. So SSP has only one face polished, and the back side of it is it's etched, and it is not as smooth as the top surface, while DSP has both face polished. Okay. Now how to choose among this? Okay. It's very simple. See, if you do not have to fabricate anything on top of it, okay, on the bottom of it, I will use only single side polished wafer. Okay. But if I have to do fabrication on the back side also, okay, I will use a double side polished wafer. Okay. Let's understand this with the same example of gas sensor that we are seeing from the first lecture. Okay. So I have a silicon wafer. I have oxidized it. Okay. My oxidation is done on top of this. Okay. Now I will do IDE fabrication on top of it. Okay. So I have fabricated IDE, or let me draw it once again. Okay. So I have a silicon wafer. Please note that there is some oxide that I have grown on top of this. Okay. Now I have fabricated IDE by some photolithography on top of it. These are two probes for contact. Okay. And these are platinum or gold metal lines, the fingers of IDs. Okay. Now this device is used for room temperature measurement. Okay. This is room temperature measurement. All right. Now say if this gas sensor has to be operated at higher temperature, say at 200 degrees Celsius. Okay. It means that there should be some heater that has to be integrated with this. Okay. This kind of device for room temperature, I can use a single side polished wafer. It is more than enough for me. Okay. However, say for example, I want to fabricate heater, platinum heater at the back side. You have already seen the platinum heater in one example where I have shown you a silicon chip. Okay, so this is a spiral kind of a platinum heater that I want to fabricate at the back side of the wafer. Okay, for that I have to do litho on the back side of the wafer also. Now my SSP will not work over here, okay, because the back side of it is only etched, it is not polished. Please note that lithography will only be successful at the polished side, because polished will remove any kind of micro defects or say small cracks on the surface. Okay, this etched back side will have lot of roughness, okay, and lithography will be unsuccessful on that. Okay, so for high temperature gas sensor fabrication, I need this IDE to be fabricated at the back side. Okay, and for that I have to do litho on the back side also. Therefore this SSP will not work and I have to use a DSP. Okay, so the thumb rule is that for a microsensor fabrication, if you think that in your process flow, if the fabrication is only at one side of the wafer, okay, you go with SSP because it will reduce the cost of your wafer. Okay, however, if you have to fabricate on the other side also, you have to go with the DSP. Of course, this will induce some extra cost. Okay, now I know that which side of polished wafer I need. Okay, then there are some options in the market where you do not have to buy only the bare silicon. Okay, nowadays coated wafers are also available. Okay, in my previous example also I have mentioned that you have a silicon wafer, on top of this you have a silicon oxide. Okay, means my wafer is coated with the oxide. Okay, so coated wafers are a subset of silicon wafer where either one or both surfaces have been coated with an additional material. Okay, this additional material can be oxide or any other material, we will see in the subsequent slides. Okay, this coating thickness will vary anything from micrometer to angstrom level, okay, depending on criticality in your fabrication. Okay, one typical coating is a oxide coating, and this oxide typically silicon oxide. Okay, this can be thermal oxide coating. This thermal oxide coating will always present on both the side of your wafer. Okay, other oxide coating methods include dry oxide, which produces a thinner oxide layer but with a higher uniformity of the film. There are some deposited oxide also. Please note that I am using two words. One is thermal oxide, which is grown, okay, which is grown in the silicon itself, and another is some deposited oxide, okay, which is deposited from external precursor source, okay, which is say some method by like chemical vapor deposition. Okay, so here you can see PCVD oxide, which is plasma enhanced chemical vapor deposition oxides. This produces a coating on a single side of the wafer. Okay, say if you are using a SSP and you do not need oxide on the back side, okay, PCVD oxide is fine for you. Okay, thermal oxides are grown grown on silicon, grown from silicon, okay, in some furnaces at around 900 to 1200 degrees Celsius depending on the process and precursor. Okay, I can have only oxygen to produce a dry oxide, to produce a thin oxide, and I can also have a water precursor H2O vapors where I will end up having thicker oxides. Okay, so but of course it will have on both the side, it will grow on both the side because it is growing from silicon itself. Okay, so if I have this silicon, okay, I am keeping this in a furnace at 900 degrees Celsius in some certain control ambient. Okay, I am consuming a little bit of this, some portion of this, and from this portion only this oxide is grown. Okay, so this oxygen is actually diffusing into this silicon, okay, and it is oxidizing it, okay. So you are getting a SiO2, okay. So you have thermal oxide grown wafer available directly in the market, okay. If you want only one side deposited oxide, you have PCVD grown oxide, silicon oxide grown wafers also available in the market. Sometime in the fabrication you need nitride coating, okay. Nitrides are sometimes very essential in fabrication of this microsensor. This is another type of coating that is available directly on silicon. So you do not need sophisticated instrument to grow nitride if you already know that what thickness of nitrides you need on your silicon. Usually these nitrides are this silicon nitride, okay. Silicon nitride offers different mechanical and chemical properties to oxide layers. Mostly they are used in low cost method. I am not discussing low cost method here, but if you are interested you can go and read about it, okay. Nitrides are mostly deposited by PCVD and LPCVD. This is low pressure chemical vapor deposition or low stress LPCVD, okay. Depending on your choice of nitride thickness, you will get, and the quality of the film, you will get either PCVD or LPCVD grown wafers in the market. Then third type of wafer that you can choose is a SOI wafer. Nowadays the silicon on insulator wafers are very popular, okay, particularly for optical devices. Just have a look on the SOI wafer, how it looks. So this is a silicon, this is again a silicon, and in between you have buried oxide layer, okay. This is known as device layer, this silicon is known as handle layer, and in between you have a buried oxide layer, okay. So SOI wafer make use of silicon insulator, silicon kind of substrate, okay, and they are used for specific applications where reducing parasitic capacitances in device is very crucial, okay. Particularly this has seen grown interest in silicon photonic based devices, okay. So I hope that by now it is clear to you that what is how to choose a good silicon wafer, okay. Then I am not discussing the stretchable part here, but if you need flexible devices, if you are fabricating some flexible devices, I have already shown you that there are couple of options you have, like your PET substrate, polyimide sheets, and so on, okay. If you need stretchability also along with flexibility, you have to go with PDMS. Then there are options on say fabrics and paper as well, okay. So there are some advanced topics, and it is not possible to cover all these substrates here, but I hope that how to choose a silicon wafer is pretty clear to you, okay. Now once I am able to choose a silicon wafer, the next step is its cleaning, okay, because I have to do photolithography on top of it, so I have to actually clean it, okay. But before cleaning, I should know that what kind of contamination my wafer can have, okay. This contamination can be organic in nature, metallic in nature. It can have some native oxide already grown on the surface, and it can also possess some micro roughness even it is polished, okay. The source of organic contaminants are from our body itself, say during its handling and all. Some skin oil can come on top of it. It can have some resist already there or traces of resist already there if this is some used wafer already, okay. There are some polymers which can exist on the wafer during handling and all, okay. Metal contaminants again come from our sweat and all, like sodium, potassium, those kind of contaminants you can always you know, expect on the wafer of on any kind of wafer, okay. Then some heavy metals, transition metals, those kind of things also come from ambient or the transition through which this wafers goes through. Okay. Native oxides are always very common. They are very thin, like less than 10 nanometer or so. Okay. And silicon has this kind of tendency to form native oxides. Okay. However, for your fabrication, these native oxides also you have to minimize. Okay. Otherwise, it will hamper your process flow. Okay. Micro roughness is something which is present because of handling again. So you use tweezers in the laboratory, okay, or sometime you even if you are wearing gloves, you are handling it with hand, okay, of course with some gloves. Then also it can induce some micro roughness. Okay, so wafer cleaning provisions are very important to know. Okay, there are 3 levels of contamination control. Okay, level 1 is clean room. Okay, where clean room will see what it is. Okay, this is the place where you are going to actually fabricate your sensor. Okay, level 2 is wafer cleaning, actual wafer cleaning, and level 3 is getting. So we'll see all of these in brief. Okay, so what is a clean room? Okay, so a clean environment which is designed to reduce the contamination of processes is known as clean room. Okay, but this definition is again very broad. Okay, so I mean we have to understand that what is a clean environment, what is a clean room that are desired for our sensor, that is required for our sensor. Okay, so a clean room is a room in which the concentration of airborne particles is controlled. Okay, this is done by minimizing the introduction, generation and retention of particle in that particular room. Okay, apart from the control of these particles, the physical parameters of the ambient should also be controlled in the clean room. Okay, these physical parameters are temperature, humidity and pressure inside the room. Okay, these all are required for better fabrication of the device. Okay, so this control is done by airflow control in the clean room, by filtration using HEPA filters and other advanced filters. Okay, by using the material selection, the proper material selection protocol inside the clean room. Okay, then there are some user protocols that has to be followed inside the clean room. We will see some of the protocols, and of course by cleaning. Okay, the clean room control, I mean the physical parameters which you have to control inside a clean room again are temperature, humidity, sound, lighting and vibration. Okay, so temperature and humidity, we know that they should be constant. Say if my process can allow 50% RH, RH is relative humidity. Okay, so my clean room's ambient humidity should not go to 52% or 48% RH. Okay. Similarly, the temperature, if I want my process to happen at 20 degrees Celsius, okay, it should be fixed at 20 degrees Celsius. It should not go to 21 or 19 degrees Celsius. Otherwise, I will see the structure, change in the structure. Okay, sound is very important. Okay, so if I am doing the fabrication at a place where there are a lot of sound, okay, my device structure can get hampered. Okay, then lighting is very crucial inside a clean room. Say if I am using a light source of say 190 nanometer, okay, and my bulb that I am using inside a clean room, it is also producing a wide band gap, a wide range of spectrum. Okay, say something from 130 nanometer to say 700 nanometer. Okay, this light can interfere with my light that I am using for exposing my resistor or something that I am using in lithography. Okay, it will damage my structures. Okay, so lighting inside the clean room is very crucial. So mostly you might have seen clean room ambient to be yellow. If you search in Google also, you will find the clean room, the photolithography section of clean room to be yellowish in color. okay, because we use mostly UV light for this exposure. We'll see in brief about that, okay. And then vibration is another factor that is very dangerous for the fabrication. If say I'm fabricating it on a table which itself is vibrating, okay, my structures that I have planned will not be as correct as I have intended, okay. Therefore all these parameters has to be controlled in a clean room, okay. So there are some standard definitions of clean room, okay. I can have class 1, class 10, class 100, class 1000 and so on class of clean room, depending on how many particles of 0.5 micron or bigger exists in 1 cubic feet of area, okay. If I'm expecting only one particle, okay, which is very difficult to control, I can say that I have a class 1 clean room, okay. If the particle number of particle is 10, I can say that I have a class 10 clean room, okay. If the number of particle is around 100, I can say that I have a class 100 clean room, and so on. Please note that these numbers are very difficult to achieve, okay. So just by decreasing one number, the number of filters that I have employed, type of filters that I have employed, the direction of flow, direction of air flow, all these things will change, okay. So it's very difficult to achieve these numbers, okay. However, I mean there are you can achieve this by certain efforts and using certain amount of filters, okay. Inside clean room, how to work, because that is the place where you are going to fabricate all the sensors that we are going to discuss in this course, okay. So there are certain protocols at every stage, okay. There are number of protocols. I have listed some of them. Like there is some gowning protocol. You cannot walk inside a clean room just by wearing a pant and shirt or by wearing a regular cloth, okay. So you have to do some gowning before entering into a clean room, so that, because man itself or you are itself a biggest source of contamination for the device that you are fabricating, okay. So you have proper gowning protocol for this. Then how to enter into clean room? Can I simply walk inside a clean room? No, okay. There are some entry protocol for walking inside a clean room or for entering into a clean room. Then how to use the equipments that are available in the clean room, okay. I can have different segregated equipment positions. How to reach all those positions, how to use them, you have certain equipment using protocols, okay. For wet bench, where you handle different acids and bases, you have different protocols. For using very hard acids like HF, you have separate set of protocols, okay. They can damage your body like anything, okay. If it is spilled into ice, I mean the conditions became worst, okay. Therefore you have different protocols for handling these acids, okay. How to communicate with your friends inside the clean room, or how to communicate with outer environment when you are inside the clean room. You cannot simply use your mobile phone to call your friends, okay. So there are certain set of communication protocol inside the clean room, okay. And most importantly, safety protocol, safety of yourself as well as safety of the equipments that are inside the clean room, okay. So you have chemical handling protocols, disposal of chemical protocols, chemical spill protocols, and first aid protocols, okay. And apart from this, there are various other protocols also available inside the clean room, depending on where it is located and what class of clean room it is, okay. So for gowning, you should wear face mask, hairnet, a gown. These are known as mostly bunny suits. You have shoes and gloves. You have to wear them in particular order, okay, and that order has to be followed exactly, okay. Similarly, in the degowning process, you have removal of gloves, shoes, your gown, hairnet, and face mask, okay. This is very crucial, Okay, so degowning has to be also done in proper format. It is not that you first take out hairnet and in the next time you are taking out your face mask first. Okay, for every clean room there are certain set of standards. Okay, so there are certain set of gowning protocol. You have to exactly follow that. Okay, after gowning you can step on the sticky mat and push the doors of air shower, where you can actually enter into some area where you can take a air shower. Okay, so entering into the clean room has different set of protocols. Okay, you should have a clean hand, a clean face and clean clothes to enter. Okay, you have to wear proper clothes, particularly you should avoid fur kind of materials in your shirt. Okay, you should avoid any kind of decorated accessories like gold chains, gold bracelets and all those kind of things. Okay, they are biggest source of contamination inside the clean room. Okay, if you are suffering from a cold, cough and other things, you should avoid going inside the clean room, because if you sneeze inside, okay, you not only damage your own device, but you will also end up damaging other people devices that are getting fabricated inside the clean room. Okay, you cannot bring any tool from outside and walk inside the clean room. Okay, you should not bring any tool from outside. Eating and drinking inside clean room is strictly prohibited, be it any clean room. So bringing food items and drink items are not permitted inside a clean room. So there are other entry protocols also, like tailgating is not possible. Okay, bringing guests are not allowed. So it depends on clean room to clean room. Okay, there are then equipment using protocols, where use only if you know the instrument, how to operate it. Okay, so there are certain laboratories where you have dependent users and independent users. Okay, dependent users are those who can work only in presence of some independent users, and independent users can use the instrument without taking permission from any independent user. But then also it is advised that they follow buddy system, means when you are inside the clean room, you are using some instrument, someone should be there accompanying you. Okay, although you are operating the instrument alone, and someone from outside also should know that you are working today inside the clean room. Okay, if there are a lot of lasers that your instrument has, okay, if laser is on, it is always advised to wear laser glasses, laser protection glasses. Okay, proper PPE kits has to be wear. Okay, personal protection equipments has to be wear when you are working on wet bench area. Okay, wet bench areas are those where you actually do some liquid processing. Okay, so you have a certain set of wet bench protocols, like you have to wear the aprons, safety glasses, face shield and appropriate gloves when you are working on this acid. When I say appropriate gloves, means for different acids, sometimes you have different gloves designed. Okay, so you cannot say if I have say X, Y and Z kind of gloves, okay, I cannot use it for all kind of acids. Okay, I can, it may be the case that I have to use this glove X for acid A. X cannot be used for another acid B. Similarly, Z can only be used for another acid C. Okay, so before entering into the clean room and before using the wet bench, you should know that what kind of gloves you have to wear specifically for the acid that you are handling. Okay, also please note that you have to check the exhaust working, the exhaust system is working inside the clean room or not. Okay, because I mean, it can be sometimes very dangerous to work when the exhaust is not working, because sometimes the reactions are so exothermic that you have lot of fume and other volatile organic compounds getting emitted in the process. Okay, and they can damage our internal systems. Okay, Then for using acids, you should know the PPE kit that you are wearing. Okay, to handle hydrofluoric acid or buffered hydrofluoric acid, F Teflon kind of thing has to be weared. Okay, so HF is the dangerous thing inside the clean room. In fact, it is the most dangerous thing liquid that you are going to use inside a clean room. So how to handle this HF you should know beforehand. Okay. Similarly, for communicating inside the clean room is very crucial. How to communicate with your friends. Okay, usually you should not open the door of the clean room for any kind of communication. Okay, so it's not that simply you will open the door and ask the outsider that, okay, I have this problem. No. Okay, there are certain set of protocols that you have to follow. Okay, there should not be use of any mobile phone. You have designated landline phones inside the clean room, and you should always contact your building management system through those phones only. Okay, as I have already mentioned that for any kind of guests are not allowed in the clean room. If the person is not trained, he should not be brought into clean room. Okay, there are certain set of safety protocols for chemical handling and disposal of these chemicals, and in the case of chemical spilling. Okay, for chemical handling, you should know that you have to use fume hood. Okay, if you are not using fume hood, you are using it on a normal bench. Okay, you are keeping the life of yourself as well as others in danger. Okay, so you should know the use of fume hood. You should be very careful while making chemical composition. Okay, like add acid to water or water to acid. It should be very clear to you. Okay, appropriate gowning should be there. How to handle the fluoride. Okay, fluoride handling is very crucial. You cannot use fluoride in glass beakers because fluorides etch the glass. Okay, therefore they should be always placed in plastic bottles. Okay, these things should be very clear to you before you actually use the wet bench area or you basically use any chemical. The MSDS file for the chemical should be clear to you that if the material is carcinogenic or it can have any other kind of health hazard and all. Okay, then disposal of these chemicals. Okay, so now when you have used the chemical, okay, how to dispose them. Okay, so you have to be very crucial, and you should be very smart while selecting this disposal methods for acid, base, fluoride, organic solvent and other users. Most of the laboratory has a centralized way of collecting this wastes. Okay, but then also say if there are certain bottles inside the clean room where you have to pour the waste acid or base. Okay, so you have to be very careful that if your acid is very concentrated or if your acid is very harsh, can you add this to certain bottle? Check it twice if you can keep it there or not. Okay, so disposal of these chemicals are very crucial. Okay, in case of chemical spill, first of all, you should not be in panicking situation. Okay, if it is spill on some person, you have to follow adequate showering steps and seek medical attention. The showering steps can be, say, taking first washing your eyes with the shower and then taking a bath, or if it is spill on the floor, you have to be very smart that if the spill is very small amount or it is very large amount. Okay, accordingly you should take decisions. Okay, and of course in emergency you should be smart enough or quick enough to use first aid kits that are available inside all the clean room. Okay, so now when I know that what are the protocols inside a clean room and how to use this clean room, okay, I am ready for the next step, which is cleaning of my wafer. Okay, so in the next class we will learn how to clean these wafers and little bit on getting. Okay, and further we will move towards photolithography. Thank you.